In this episode, we are going to solve a problem on series parallel using KCL and KVL, Kirchhoff's current law and Kirchhoff's voltage law. So we have a problem, and this is our diagram with some parameters given. So based on the idea of Kirchhoff's current law that we treated in the previous episode, and the Kirchhoff's voltage law, we are going to combine the ideas and solve this problem. So the problem is, from the figure below, determine I2, which is our current 2, I1, VR1, that is the voltage across resistor 1, and VR3, that is voltage across resistor 3. So looking at our diagram, this is our resistor 1. We have resistor 2 also here, resistor 3, and the fourth resistor. So we are given some parameters to calculate for the other missing parameters. When we look at the diagram, we have a 6 ampere or 6 amperes current here that is moving, and we have resistor 2, and a 40 volt is measured across resistor 2. And when you look at resistor 4, we measure a 30 volt voltage across the resistor. So taking all this into consideration, let's start solving the problem and see how best we can get our answers. So we should find I2. I2, this is I2. Yes, and this is I1. What can we say for finding the value or the current for I2? What can we say? When you look at the current I2 that is flowing through resistor 3 and flowing through resistor 4. Now, when you get to this point, you see that the measured current was 2 amperes. And we know that the same current, since the resistors are in series, the same current I2 is flowing through them. And if it is measured 2 amperes here, then definitely the current that started flowing from the junction through resistor 3 and resistor 4 is going to be the same as the 2 amperes. Are we getting that? Because they are in series, there is no division of current. So let's write that for our current I2. So our solution. So the A part, the current I2 is equal to the 2 amperes current, that is from the figure. We just got the answer from the figure. Looking at the branch, let's call this branch A, B. So looking at the branch AB, you can see that the same current is flowing through. And if we measure it to be 2 amperes, definitely I2 is also 2 amperes. Now let's look at the B part, which says we should find I1, current I1. So how are we going to find the I1 current? Now, from the figure, what do we see for the B? We can also see that there is a 6 amperes current here that is flowing through the circuit. And this is telling us that at this junction, the combination of the current that is leaving here is what? 6 amperes. Is that true? Yes. So if the combination of currents leaving, because this I2 is coming this way and I1 is also coming this way, and the leaving current is 6 amperes. So we can use the KCL, Kirchhoff's current law, at a node, which states that the current moving inside a node is equal to the current leaving the node. Are we okay? So we can consider the current coming and the current leaving. So let's call this at node C. So at the junction or node C, what do we see? Applying the KCL, we can see that current entering, that is I2 plus I1, should be equal to the 6 amperes current leaving. Is that true? Yes. And we also have the value of I2, which is going to be 2 amperes plus I1 equal to 6 amperes. Definitely our I1 is going to be 6 amperes minus 2 amperes, and that is going to give us 4 amperes for the I1. So we have the answers there. We can move to the second part and also find our value. So the C part is asking us to find the voltage across resistor 1. The voltage across resistor 1. So this is resistor 1 and we want the voltage across it. Are we good? So let's make some analysis with voltage or Kirchhoff's voltage law. What do we see? This is a 100-volt source. Are we okay? So as the voltage is working on resistor 1, there will be a voltage drop. That's what we are going to consider. Now, if resistors are in series to each other, what do we know? We know that the voltage is the sum of them. If we have two resistors, say V1 and V2, and the total voltage is, say, 200. Therefore, our V1 plus V2 should be equal to 200 if they are in series. Now we remember that. Let's apply that idea to the diagram and see how best we can solve this. When you look at resistor 1 and you look at this whole part, what do you see? So resistor 1 and the whole part I have circled, we can combine everything here in the circuit part to be in series with resistor 1. If we are going to find the final resistance, then we will solve this in series, remember, and we will combine it with this as parallel. Then the final answer will also be in series with resistor 1. So with that idea in mind, we can see that resistor 1 is going to be in series with the final resistance over here. Is that true? And if the summation, let's call voltage across resistor 1 as V1, and everything across the final resistance here to be, let's say, V2. Okay, so we call it V2. They should sum up to the 100 volts, right? Now, if we have, say, this resistance, the V2, now we know that the voltage across R2 is 40 volts. 40 volts, and it is in parallel to all these parts, and we know that parallel circuit have the same voltage. Are we okay? So now we can say that V1, this expression is true. Our V1, voltage across resistor 1, plus our V2 should be equal to 100 because it will be in series with our V2. Is that clear? Is equal to 100. And what do we see for V2? We saw that V2 has 40 volts. And if it is 40 volts, then our V1 will be plus 40 equal to the 100 volt. And V1 can be calculated as 100 minus 40. And that will let our voltage across resistor 1 to be 60 volts. So voltage across resistor 1 is 60 volts. That is very clear. Now we go to the D part, which says voltage across resistor 3. Let's look at how we can get voltage across resistor 3. This is resistor 3. Let's look at it. So the D part. Now, when we study the diagram, we are going to see that resistor 3 and resistor 4 are in series and they are parallel to resistor 2. So for parallel circuits, we say the voltage across resistor 2 here is equal to the summation of the voltage across resistor 3. So this is resistor 3 and resistor 4. Because we assume that since this is in parallel to resistor 2, whatever voltage is across resistor 2 is equal to whatever voltage across the two of resistor 3 and resistor 4. So this is the expression. And the question is saying the voltage across only resistor 4 is 30 volts. And we know for resistor 2 to be 40 volts. So we are going to say our 40 volts is equal to V3 plus resistor 4, which is 30. And our V3 should be 40 minus 30, meaning V3 is 10 volts. So you can see that the summation of voltage of resistor 3 and 4 should give you the one across resistor 2 because they are parallel. So this is the solution for the problem using KCL and KVL. Let's look at example 2. So example 2, this is our problem. Using the figure below, find I2, V2, R3, V1, R1, R4. So a lot of parameters for us to calculate. Now this is the diagram. We have resistor 1 and resistor 2, 3 and resistor 4. We have voltage across resistor 4 and we also know the various current movements. So now we are seeing a 0.8 amperes current from the source. So the total current produced coming out from the source is 0.8 amperes. So let's look at how we can solve the problem. So first we have to find I2 and this is our I2. Let's look at it. So solution. What can we say for the A part, I2? Now when we look at the diagram, at this point junction using the KCL, the current entering should be equal to current leaving. And what is the current entering? This is the 0.8 current entering the node. And there is a 0.3 amperes leaving and I2 is also leaving. So based on the KCL, we can solve this. So our expression is going to be current entering, which is 0.8 amperes current, should be equal to current leaving, our I2 plus 0.3. And from here, our I2, that is going to be 0.8 minus 0.3. And that is going to give us 0.5 amperes for I2. This is solved using KCL. Now the B said we should find the voltage across resistor 2, which is V2. So voltage across resistor 2. Now we know the current I2 that is passing through resistor 2. We know the resistance of resistor 2. So clearly from the Ohm's law, we are going to say V2 should be equal to I2 multiplying R2. Is that true? So our V2 is going to be I2, which is 0.5 multiplying R2, which is also 100 ohms. So this is going to give us 50 volts. So This is the voltage across resistor 2. Now, let's look at the C part, which says R3. We should find the resistance R3. So the C. So what do we see here? We have to do some analysis so that we can get R3. We can also get R3 from the expression that we know V3 should be equal to I3 multiplying R3, right? So we know I3, which is the same as our I3, which is the same as the 0.3 amperes. So the current moving through the third resistor. Do we know the V3? No, we don't know. But yes, we also know. We know that resistor 2 is parallel to resistor 3, and for parallel arrangement, the voltage is equal. For parallel arrangement, we have the same voltage. So can we say our V3 is equal to V2? Yes, that is true, because V3 and V2 are equal due to the parallel arrangement. So now, which is equal to the one we calculated, 50 volts. Therefore, our R3 is equal to V3 on I3, which is going to be 50 on 0.3, and that is going to give us resistance of R3 to be 166.7 ohm. So we have the third part. Now the D, which says we should find V1, voltage across resistor 1. Voltage across resistor 1. So let's look at the analysis. Pay attention here. So voltage across resistor 1. What can we say here? Now we know the total voltage coming from the source, which is 100 volts, right? So the 100 volt should be equal to the summation of voltage at the resistor 1, V1, now plus voltage at resistor 4, which is V4. You know that when you combine resistor 2 and resistor 3, you are going to get a series connection with R1 and R4. And remember, the same voltage is across resistor 3 and resistor 2. So the same voltage for the combined resistance. So that is also going to be plus. Let's call the summation of, or the resultant of, R2 and R3 as V0. That is going to be. So when you sum the voltage drop across resistor 1 and those across resistor 2 and 3 and across resistor 4, you are going to get the total voltage. Now we are finding for V1. We know that, so 100 should be equal to V1 we are looking for. V4 we have 30 volts given, and V0, which is the voltage across resistor 2 and 3, and we know that that is equal to 50 volts. So plus our 50 volts. So we are going to get our V1 equal to 100 minus 50 minus 30, and our voltage 1 is going to give us 20 volts. So there is 20 volt drop at resistor 1. Now the E, which is talking about R1, we should find the resistance of the resistor 1. Let's look at it. This is quite simple. So E, R1. Can we say R1 is equal to, from the expression V1 on I1? That's the Ohm's law. Yes. And we know V1. Yes, we just had V1 to be 20 volts. 20 volts. We know I1, which is the current flowing through the resistor 1. Yes, that's the 0.8 ampere, 0.8. So with this, we are going to get our R1 to be 25 ohms. Very good. Now the last part, which is the F for R3, 4. And R4 is also going to obey the same principle, V4 on I4, which is going to be, now voltage across resistor 4 is given as 30 volts. And what is the current in resistor 4? The current moving is going to be the summation of current from I2 and this 0.3. And we know that at this junction, if 0.5 is coming and here is bringing 0.3, therefore there will be 0.8 current, which is the same as the starting current moving through resistor 4. So that is also going to be 0.8, and this is going to give us 37.5 ohms. So this is the solution for the problem. Thank you for watching this episode. Please subscribe to the channel, comment, and share the video. See you in the next episode.